Hi everyone, in this video as part of the STEManuary project, I'm going to be discussing the photoelectric effect. This is the observation that when electromagnetic radiation is incident on the surface of a metal, electrons can be emitted under certain conditions. And it was observations based on this effect that led to some key early breakthroughs in the development of quantum theory, which is needed to describe physics on the smallest possible scale, so subatomic scales. And one key part of quantum theory is the so-called wave-particle duality. So the observation that under certain circumstances we need to consider light as behaving as a particle and being made up of packets called photons, and also that in turn particles can display wave-like characteristics. And I'll be talking about the first part of this, the idea that we often have to consider light as being made of particles called photons, throughout this video. So there were several observations of the photoelectric effect that were incompatible with the classical model of light as being made of just electromagnetic waves. And around 1905, Einstein postulated that actually light should be considered as photons, so particles with an energy proportional to their frequency. In 1914, a scientist called Robert Millikan performed a very famous experiment that tested Einstein's model of the photoelectric effect, and it was found to support his hypothesis. And actually, in 1921, Einstein got his Nobel Prize for his work on the understanding of the photoelectric effect, which I actually find quite interesting, since he got his Nobel Prize for something other than the theory of relativity, which is what he's actually more well known for. Okay, so those of you who've already studied this, as usual, this is a great time to pause and jot down everything you can remember about the photoelectric effect before we get started. And otherwise, I'll share my whiteboard and we'll get going. So the photoelectric effect, as I said before, is the idea that if we have electromagnetic radiation incident on the surface of a metal, then we can get electrons being ejected. And there were several observations of the photoelectric effect that couldn't be explained by the classical theory of light, which I'll go through now. So the first is that for a given metal, if the frequency of the light was below some threshold frequency, then actually no photoelectrons would be emitted at all, irrespective of the intensity. So no photoelectrons. The second was that actually, although the photoelectrons being emitted had a range of different energies, there was always a maximum kinetic energy. So the maximum kinetic energy that again was proportional to the frequency, assuming that the frequency was above its threshold frequency. And to measure the maximum kinetic energy, the experimental setup typically involves applying a potential difference across the gap in which the electrons are being emitted, and you can work out the kinetic energy being equal to E times the stopping voltage, where the stopping voltage corresponds to the potential difference you need to apply such that you get no photoelectrons being detected at a given point. So the final observation was that if F was greater than the threshold for frequency, then the number of photoelectrons depended on intensity. So if you had higher intensity incident light, you would get more photoelectrons being released. And I'll now discuss why this model isn't really consistent with the classical wave model of light. So if we consider the wave model here on the left-hand side. So for the classical model of light as waves, we know that the energy oh dear. The energy being transported by a wave is proportional to its intensity. So inside a metal, electrons have a range of energies, but we can define the work function which I'm going to call phi, as the minimum energy required to free an electron. So this is equivalent to the energy required to free the most energetic electron inside the metal. So in the classical view, because energy is incident on the surface through waves, what could happen is electrons inside the metal could gradually absorb energy from the incident radiation until they had enough energy to escape. And in that situation, you might expect that for low intensity light, you'd actually have a time delay whilst the electrons accumulated enough energy to be able to escape. However, this wasn't observed in the experiments, and actually, provided the frequency was above the threshold frequency, it was typically observed that photo emission was instantaneous. The other thing is, in the wave model, the energy of the incident radiation depends on the intensity, but doesn't depend on the frequency. So again, this isn't compatible with the set of observations we have on the top right-hand side for the photoelectric effect. So now let's look at the quantum model of light. So this is going to be on the right-hand side. So in the quantum model, light is actually made of photons with an energy, I'll call it E, equal to h times f, where f is the frequency and h is a constant called Planck's constant. An important thing to be aware of is Planck's constant is a really, really small number. It's of the order of 10 to the minus 34. So that means that actually we only really see quantum effects when we go to very small length scales, which is why we can, do most of the physics about day-to-day objects using the classical rules and ignoring quantum effects. So in this quantum model, we can explain all of these observations because the threshold frequency, so h times f threshold, will just equal the work function. So in the quantum model, a single electron will be emitted by a single photon being absorbed. So we assume they only absorb one photon at a time. So that means that if that photon has enough energy to overcome the work function, then it will escape. So the threshold frequency can be directly written in terms of the work function. So the kinetic energy, which I've said before, which the maximum value of this is measured by the stopping voltage, can then be written in terms of the frequency and the work function. So E times the stopping voltage will be HF, which is the energy of the photon, minus the work function. So this is the energy, the kinetic energy the electron has left once it's been freed from the metal. To explain the final observation, all we have to realize is that in the quantum model, the intensity will be proportional to the number of photons incident. So again, if the intensity increases, then the number of photons incident will increase. And again, provided they have a frequency high enough to free the electrons, then you'll get more photoelectrons being emitted. So as I said before, this was a really pivotal experiment in the development of quantum mechanics, which is something that I'm sure those of you who go on to study physics more at university will learn a lot more about. In the meantime, I hope you found this video enjoyable, and please continue to email requests or questions if you'd like to discuss anything from this further. In the meantime, thank you very much and have a nice day or evening.